Okay, let's resume. It's our pleasure to have Konstantin from ETH Zurich to tell us about high-dimensional Hoffman.
I am. Thanks for the invitation and for the introduction. Yeah, I'll be talking about high-dimensional Hoffman bound and its applications to extremal combinatorics. And this is based on a joint work with Yuval Filmus, who is in the audience now, and Noam Lifshitz. So let me start. So the structure will be like so. I'll talk a little bit about the Hoffman bound for graphs, which is classical stuff, and then I'll talk about its high-dimensional generalization, which is a similar bound for hypergraphs. Okay, and yeah, feel free to interrupt if you have any questions. So first, what is the graph? Usually, it would be vertices. Some of them are connected with edges. In our case, it will be an undirected weighted graph, meaning we have a finite set of vertices V, and we have probability distribution on undirected edges where loops are allowed. So as I said, there's funny power of 2, which means all 2 multisets of V. And the edges are just the support of mu. So every pair which has non-zero measure. And this kind of measure on edges, it induces a measure on vertices, like so. It basically says that we choose an edge with respect to the measure mu, and then we choose one of its vertices uniformly at random, meaning each one with probability half. It may happen if we have a loop from V to V, then we choose V. So this is what is written here, and we'll be interested in the independence number of X. That is, we look at all independent subset of vertices of V, meaning subsets of vertices which do not contain an edge, and we look at their measure and ask what is the maximum measure of this. Any questions so far? That's good. Looks good. So we're here in the algebraic methods section. So a method of bounding the independence number from above will be algebraic. So we'll define an adjacency operator and then we'll work with its eigenvalues. So first we define the inner product on functions on vertices with respect to the measure, and it's exactly what you think it should be. So given 2 functions f and g, we take their product, we take the product at each vertex, multiply by the measure and sum this thing up. That would be the inner product. And the normalized adjacency operator on this space would be this scary thing, which is basically it. We for each function we sum the values over the neighbors of each vertex, weighted by the measure. And if you're used to thinking about adjacency operators in terms of matrices, then the matrix for this operator, which is indexed by the vertices, it has this thing at the place uv. So on the diagonal, we have the measure of the vertex of the loop divided by the induced measure of the vertex. And if it's not the loop, then there's the typo. We'll take the measure of an edge divided by twice the measure of u. So it means that in every row, the sum is 0, or the sum is 1. So in particular, this thing is the self-adjoint, has real eigenvalues within the interval from -1 to 1, and the constant function is an eigenfunction whose eigenvalue 1. Okay.
So it's like a matrix for the random walk, basically, right? Or
yeah, I think so. Let me think. Yeah.
Where the transition is proportional to these weights, transition probabilities.
Yeah. Yeah. Exactly. Yeah. Good point. So now the Hoffman bound, which is so it basically says that the independence number, so the measure of an independent set, cannot be larger than this amount, this value on the right, where lambda mean is the smallest eigenvalue of the adjacency operator. So this theorem is usually attributed to Hoffman. He himself proved it for an adjacency operator, non-normalized adjacency operator for graph. Some people attribute it to Delsart, but I think it's in general a very classical result by now. Yeah, so the proof is the original proof is kind of sophisticated, but there are different proofs now, and it's nothing more than linear algebra actually. And I once tried to teach it in a linear algebra 1 class, undergrad. It was it's possible, I think, but I failed. So yeah, students didn't like it. But I think
in which country?
In Israel, it was at Bar-Ilan University. Actually, it was linear algebra. No, it was discrete math for electrical engineer students, but they were good. But still, yeah. So I thought it could work, but I still think it could work. I just didn't do it well enough. Anyway, so it's not a hard proof, and I think so. It's basically linear algebra. So what it's good for? This bound. One thing you can prove Erdős-Corrado theorem. That's a nice application of it. So I guess it's no need here in this audience, but I will do it anyway. So what is Erdős-Corrado? It's a theorem that says that if you have a family of case subsets of an n set, where any two subsets in this family intersect, then the size of this family cannot be larger than this. Then n-1 choose k-1. So this bound is sharp because if you take all k subsets that contain a fixed element, then there will be this number of them, n-1 choose k-1. Yeah, and this is the best you can do. So how do you prove it using Hoffman bound? I think this is proved by Lovash, and what you do the following thing: you construct a graph where the vertices are the k subsets, and you connect two if they do not intersect. And then every independent set would be a family where every two do intersect. So that's exactly what you're looking for. And then if you compute the Hoffman bound, so here you have a graph, you need to compute its eigenvalues, but if you do so and compute the Hoffman bound, it turns out to be exactly this: n-1 choose k-1, and this is the end of the proof. Okay, any questions here? So then Hoffman bound has another good property. So if you take tensor product of two graphs, when a non-weighted version, you just your vertex set is Cartesian product of the vertex sets, and you connect a pair with a pair if you have an edge in every coordinate. So then in a weighted setting, this would be just you take the product measure. And for a single graph, you can take its nth tensor power. And good thing about, so one good thing about the adjacency matrix of the tensor product is that it's Kronecker product of the matrices, of the relevant matrices. And then eigenvalues are exactly the products of the eigenvalues. And if you take a tensor product, a tensor power of a graph, then its minimum, the smallest eigenvalue, remains the same, because the smallest you can get is the smallest you had and multiplied by 1, because this thing is negative. So in absolute value, you can get smaller things, but you're looking for the smallest negative. So that's the thing you have. And in particular, and the Hoffman bound remains sharp. Why? Because for your independent set, you can take an independent set in one coordinate, and the rest, the whole vertex set in all other coordinates. So the measure of the independence, maximal independence set remains the same. Okay, is it good? Is it? Are we good? We're good.
Yes.
Good. Thanks. So one can prove a p-biased Erdős-Corrado. What does it mean? So now instead of k subsets of n set, we have all of them, where each subset has a measure like this. So if it's of size a, then we have p to the power a and 1 minus p to n minus a. So basically it means we have n elements, and we this probability measure means that each element would take with probability p and do not take with probability 1 minus p. And this would be exactly the measure. And we say that the measure of a family is just a family of subsets is the sum of measures. And so the question is, how large can be a family of sets be in this setting if it's intersecting? So here you can approach this problem by considering a graph G to the n, where the original G has only 2 vertices, 0 and 1. Then G to the power, G to the tensor power n would be vectors of 0s and 1 of length n, where basically then each vector encodes a subset. And you have an edge. So in the original graph, you have an edge between 0 and 1 with some weight. And you have an edge between 0, you have a loop from 0 to itself with weight 1 minus 2p. So basically, your 2 vectors in G to the n would not be connected by an edge if they, if they intersect. No, if they don't intersect. Yeah, if they don't intersect, they won't have an edge. And then Friedgut showed that, so by the same, then, in order to compute the Hoffman bound for G to the power of n, you need to compute the Hoffman bound for this graph on 2 vertices, which is like computing eigenvalues for 2 by 2 matrices. And he proved that if a family is intersecting, then the measure of the family is at most p, which exactly corresponds to a family which a family of all subsets which contain a specific element. And then the same kind of technique was applied to other problems, and the names you should look for if you're interested are Alon-Dinur-Friedgut-Sudakov, Regev, and others. So now what happens for hypergraphs? So the setting would be as follows. We now consider k uniform hypergraphs, which means we again have a finite set of vertices, and we put a probability measure on v to the k, again a typo. This is a set of all k multisets of v. So we have multisets of size k where repetitions are allowed. So it's kind of, loops. We can have loops in terms of a hypergraph, like one vertex 3 times, another 2 times, and so on. So this kind of measure, it induces a measure on v to the I for all i's from 0 to k minus 1, which basically corresponds to the procedure where we choose a k edge from v to the k with respect to mu, and then choose one of its I subsets uniformly at random. Then we'll be interested in the independence number of x. This would be the measure with respect to mu1 of a set. And we call it, the set is called independent if it contains no k edges, no maximal edges. So, you know, particularly if we talk about three uniform hypergraph, an independent set is allowed to contain, you know, pairs which belong to the same hyperedge, but not triples which form an edge. And yeah, so is setting clear here? Any questions? Good.
Does it make sense to define some other version where mu1 is replaced by maybe mu2?
Good question. It's not clear then. So, but then we would need to consider, you know, subsets of edges. And I think it's a reasonable question. And one approach might be, which might not be really good, you know, it's to construct a new hypergraph where your vertices would be the two edges and they're like, you know, so, yeah, but yeah, I mean, I think it might be useful for some questions. So we'll be interested in bounding this independence number from above algebraically. So now the question is, what is algebraically? So in order to define that, I need to define two things. One of them is a link and another one is a skeleton. So imagine we had no weights, then for an I edge in a k uniform hypergraph, we could define its link as all k minus I edges such that with their union with sigma makes an k edge. So in case of a three uniform hypergraphs, this would mean, let's say we take a vertex and ask what its link. It would be all pairs of vertices such that together with the chosen vertex, they make a three edge. And this whole thing would make a hypergraph of uniformity one lower. Is it good? Or are you with me? Good. So then in the measured case, one could say that, you know, this is basically the same thing. We take k minus I uniform hypergraph, and we somehow define a probability distribution on it based on mu. It's a bit subtle, but it's basically what I said earlier about unweighted case. You need to define the measure carefully. Okay, so this is a link for an.
Can you say what is the subtlety here?
So in order to define it properly, like we're talking about here about unordered multisets, then you would need to talk about, you know, fixed sum ordering, doesn't matter which one, and then you need to eliminate vertices one by one. So like you need to choose an ordering, and then so I mean it's like half a page. It's not really difficult, like it's not complicated, but it's like difficult to explain. It doesn't really contribute. But basically, you know, you want to look at the flags. Flag is a collection of edges of different size from 0 to k, and then you want, like, yeah, I mean.
But even if you look at normal hypergraphs, meaning like do not allow multisets, but so allow weights, then it should be probably okay. Or
yeah, I mean, so it's exactly what you're thinking about.
Okay.
So in the case of a non-weighted hypergraph where you have, like, as I said before, links. Like imagine you don't have weights, then it would be exactly this, as I said.
It's
the same as the contraction of the tensor.
Say it again.
I think it's the same as the contraction of a tensor. So you're like summing over one of the dimensions or some of the dimensions. Like you're looking at some slab and then, yeah, not even summing.
Say it again.
So like Costa said earlier, instead of thinking about it as a measure, you can think about it as a tensor. Yeah, like a d-dimensional array. And then you're just fixing some of the coordinates.
So yeah, each of your faces is you order them, so you now have a vector, like they're ordered, and then you choose. Yeah. Anyway, yeah. So procedure, a procedure. And then what is a skeleton? So for every hypergraph, you define its skeleton as just the underlying graph. So you compute its measure on the pairs, mu2, and you forget about everything else. That would be your skeleton. So for each hypergraph, you can construct such a graph. So now to formulate the bound, we'll need the following thing. For each, let's say, dimension I, you compute lambda I of x, which is the minimum over all smallest eigenvalues over skeletons over all links for I-dimensional edges. So let me go over it. So you take for each I edge of x, you take its link. It would be k minus I hypergraph. You compute the smallest eigenvalue of the adjacency on the skeleton of this link. So you get a graph, you get a hypergraph, you get a graph for this hypergraph. You compute its smallest eigenvalue, and then you take the smallest among all smallest eigenvalues for links of I edges for a fixed I. So for example, lambda 0 here, by the way, it's a link of the empty cell, which is a whole hypergraph. So lambda 0 would be just the smallest eigenvalue of the whole hypergraph. Then lambda 1 would be the smallest eigenvalues for link of every vertex, and so on. So now, taking all these lambdas, the bound goes like this. So this is the main theorem by Yuval, who's here, me and Noam. No idea what's the date. It's in the process. Maybe 2037. I don't know. So if we have a k-uniform hypergraph, then the upper bound on the independence number is this thing, 1 minus 1 over this product. Note that if you take a graph, this would mean that it's just 1 minus lambda 0, and this would be exactly the Hoffman bound. And so if all these lambdas are smaller than 0.
Wait, question, sorry, shouldn't it be plus?
No. Wait,
because all these eigenvalues should be strictly smaller than 1, right?
No, they're negative.
Yeah,
right?
well, in any case, I'm saying that this number 1 over something is a positive number.
Right.
So 1 minus a positive number would be smaller than 1.
This is good.
We're counting the measure, right?
Yeah, it's a measure. Yeah.
Yeah. Okay. That's
yeah.
fine.
Let me double check. So if we forget about numbers from 1 to k minus 2, then we have 1 minus lambda 0. That would be, yeah, it would. So it would be 1. Yeah, it would be exactly the Hoffman bound for graphs.
Yeah.
So if in addition lambda i's are negative, all of them are negative, then this bound remains the same for the tensor power of a hypergraph. So here remarks that it might happen that you come up with a hypergraph for which some of the lambdas are positive. Might happen. And in particular, this last thing means that if we start with a hypergraph for which the bound is sharp, it remains sharp for its tensor powers. And that's yeah. The proof, even more sophisticated linear algebra, I did not try to show it to undergrads. I would not do that. So applications. So I have 3 applications here. So one is a new result, as far as I understand. And it's Frankel's, there should be L here, Frankel's problem on triangle-free families. So imagine your N is within this range, and you want to know what is the largest size of a family such that it does not contain 3 distinct subsets whose symmetric difference is empty. So then the family is at most of the size n-1, choose 2k-1. And again, it is sharp because you can choose a family of containing a fixed element.
Question here, when you say symmetric difference, you mean sum modulo 2 of these 3 vectors?
I think no. So you actually want
But what is?
Yeah, so you want it's
what is the symmetric difference of 3 sets then?
It's you want it's all elements which are contained in exactly one set. So
yeah, so it's the same as sum modulo 2.
No,
because if
but
you sum modulo 2.
Yeah, you also have the intersection of all 3, which would be in what you say.
Wait.
It's a different question. I think it's a different problem also, but by Frankl.
Okay.
Yeah. So yeah, in your case, you would include those who are contained in exactly 1 and in 3. So.
But how is then this?
Oh wait,
example?
no, wait. You're right. Sorry. Yeah, you're right. Sorry. Yes. Sorry. Yes. You're right. Yes. Yes, you're right. Yeah, 1 or 3. So exactly modulo 2. Yeah. Then yeah, here you go. In the p-biased version, we're talking about vectors, and we say that the measure of a vector is a p-biased one, and we're asking about vectors of such that their sum is 0. Family without such triples. Then the measure at most p. Are we good? So yeah. So this is a new result proved with this high-dimensional Hoffman bound, and then 2 other applications. One is a funny one. So Monterey theorem from 1907. So if a graph on n vertex contains no triangle, then it contains at most n squared divided by 4 edges. You can prove it with our technique, and I'm proud to say that Alon-Dinur-Friedgut said that it's the most complicated proof of Monterey theorem known to him, which is a praise, I think. And another theorem which we reprove is that if we have a family of k-wise intersecting subsets of n, then its measure is at most p. It's a p-biased version. So these are reproved results, and let me also go to the possible applications. So one, so the original Hoffman bound, it can be applied in many settings, but its drawback that it's only can applied in settings where your constraints are binary. You're talking about constraints on pairs of things. The moment you have a problem which involves constraints on tuples, then it's not a graph problem anymore, it's a hypergraph problem. So there's some problems which we reformulate in terms of hypergraphs. One of them, I think it was mentioned here, is that how large can a subset in FQ to the n be if it doesn't contain a solution to some system of equations. You can also talk about Turing problem for hypergraphs. So how large can a family of subsets can be if it doesn't contain a specific copy of a specific hypergraph. You can also do Erdős matching conjecture. So you want, again, the size of a family, but in this case, doesn't contain S sets which are pairwise disjoint. S-wise intersecting families, so you want all S intersect, every S intersect, and Frankel's Turan problem, where yeah, so you don't want to contain a triangle, which is 3 subsets, and you want so it's what's written here: hypergraph such that each element of n belongs to an even number of a subsets ABC, meaning 0 or 2. And again, the question is how large this thing can be. So these problems can be reformulated for hypergraphs, and potentially one could maybe construct a hypergraph, compute a Hoffman bound, and see and get some bound for these problems. So and
for problem 4, the answer is known, and we also show it in the paper using our bound. The question is about S-wise T intersecting families.
So say it again.
So for S-wise,
4?
Yeah,
because I think we have it here also, right? No, wait.
I mean, this is the p-bias version, but I don't think it makes a huge difference.
Yes, so the question, what was, so I missed something?
But if you look at S-wise T intersecting families, so every S sets contain at least T elements in common. Then for S larger than 2, then it's not known.
Yes, so it's not empty, it's at least T elements, right?
But T larger than 1.
Yeah, thank you. And I'm ready to take questions.
That's
Yeah, let's thank the speaker.
So this, and following to what Yuval said, I mean, I would think that the uniform version should be more complicated than p-biased version, as it usually is, I think. And the trick there is to prove it for the optimal range of n. Of course, we know these results for some k because it will follow just from the Erdős-Corrado theorem. If say k is less than a half, right?
So
for example, for this 4.
Yes, so there's a proof using the Katona-Sekar argument, and I think it's typed. I don't remember, but I think it's typed.
Using Katonas. So you're saying that it gives. I'm not. Yeah, maybe. I don't remember now. My feeling is that it's more complicated than what you say, but maybe you're right.
Yeah, maybe I should also clarify that the idea is here that you might have guessed it, that the approach in proving this result is that you take a small hypergraph, like again on 2 vertices, for example, 0 and 1. You compute its eigenvalues, which is maybe k matrices, and then you compute them explicitly, and then you apply the bound and see if it matches. And also one thing you can do, you can play with the weights. Like there's no like you can define the weights, and this is a parameter you could play. So one trick is to choose the right hypergraph.
So maybe one more comment is that in the original Hoffman bound, you don't actually need a measure. It could be a sign measure.
Yeah. So your weights can be negative, you're saying.
Yeah, that's
Yeah.
important in my applications.
It's basically, yeah, right. If you, that's also where the lowest theta number bound comes. You basically can run over all subspace, right?
Yeah, so the lowest theta is a bit it's a bit stronger, but it's more or less the same. Yeah.
Yeah.
Mm-hmm. And how come all this link things pop up? Like why one skeleton of each link?
So the proof goes like this actually. So so you take you take an independent set and its complement, and there is a number of, so there are two edges between them, and the original Hoffman bound for graphs, it provides a lower bound on the number of these edges, so like on the measure of two edges between two vertices, and then by combining with links, and then you switch to links. So basically you bound the number of two edges between two parts from above and below. On one side you do it with a original Hoffman bound, and from the other side you do it by switching to the links, because if there's an edge going between two parts, it originates at some vertex. So that's how. So and then it's just like an induction argument.
Okay.
Because in the link you'll also have an independent set in the link. If you start with an independent set, you'll have an independent set in the link.
Mm-hmm.
Is it true that you can also generalize this theorem for non-uniform hypergraph, in the sense that maybe you want to define some filtration of mu, defined for sets of different sizes with some compatible conditions, and your proof probably will go through.
I think you could actually do that. Like if you're if the hypergraph is not uniform, then the question would be, what is an independent set? But you could define it by saying that no maximal edge is contained.
Yeah, I think as long as you have this simplex, right, then you can maybe also have a generalization.
Yeah, but then I think what one can do is, like my guess, I'm not sure. Imagine you have a triangle and an edge. Mm-hmm. You can kind of make a triangle out of an edge by including, one vertex once, the other one twice, and vice versa. Mm-hmm. This will make an artificial triple out of a duplex. And then you can think about this as a problem about uniform hypergraph. So I'm not sure if this works, but I would check this first.
Yeah. Okay. Thanks. Any other questions? All right.
This might be, I have a question.
Okay, go ahead.
This might be naive, but so Hoffman bound also has a Delsart version for pseudo adjacency matrices. Does this K uniform version also have one?
I'm not say it again. So Delsart's version has what?
So yeah, there's this Hoffman bound for that's about adjacency matrix of a graph, but you can consider some pseudo adjacency matrix where you don't have necessarily ones but non-zero elements.
That's exactly what we do.
Yeah, that's exactly the weights.
Okay.
So yeah,
I probably missed that part. I was watching this penalty shootout.
I think the Swiss lost, right?
Yeah, but for the pseudo adjacency matrix, one also allows negative entries. So
yeah,
that's what you were always talking about.
Yeah. So yeah, exactly. So you're allowed to do that. Yeah. So I think I talked about measure, but I think we could do like anything.
No. So we don't
No.
need the entire tensor to be non-negative, but we do need that after you contract it, like after you sum over one of the coordinates, then you need to get something non-negative because it shows up in the inductive proof.
Yeah. So the original thing doesn't have to be, but the links have to be.
Yeah.
Okay. Yeah. But wait, is it crucial for? I thought it's. I thought it was only important for the tensor products, like for one specific.
No.
Okay.